Hello, everybody. So I'm Nouha GAZBOUR from the French Institute of Solar Energy, INES, in France. So today we're gonna talk about alternatives toward a low carbon footprint of PV technology. So starting by the contents of this presentation, we will start by looking at the global context of the PV in the world and what is the challenge today. Then we will see the impact of the technological evolution on the environmental footprint of PV modules. Then alternatives toward low carbon footprint of PV module, how we decrease more the carbon footprint of PV modules, and we will finish by a conclusion. So starting by the global context, this is a picture that I draw just to show you what challenges the PV today are facing. So we have in one side the first aspect, which is the market evolution. We have the time running, we have the evolution, the exponential evolution of the market by China, by US, by India. In the other hand, we have the planet that we need to save by the climate change, which are suffering. So we have political pressure to install more PV modules in order to have the independency with the fossil energy. And in the other hand, we have the third aspect, which is the social acceptance. And today, the fake news. Does the PV module are really environmental friendly? Does the PV modules are green? So people ask today if the PV modules are the solution, if the PV energy is the solution today to save the world. So we will try to see one by one the aspects one by one. Then we will try to understand what is the real impact of the PV modules today. So starting by the first one, which is the political pressure, starting, for example, by Europe. So Europe has built a new plan, which is repowering Europe, which try to accelerate the installation of the PV modules in order to have the independency from Russia fossil. So the objective is to install about 600 gigawatt by 2013, so more than 500 gigawatt compared to today. On the other hand, we have the net zero emission, which is announced by the global world. And here we can see in this graph what we will expect depending on of the scenario that were published by Solar Power Europe, by IRENA, by EIA, enough toward the net zero emission. So the objective is to reach about by 2050 to reach about 14 terawatt of PV modules. Also, the US America has already also published the new era of made in US solar, and the objective is to achieve about 100% clean electricity by 2035, which means installing PV and having PV from 4% of electricity supply to 40%. So this is the first aspect, which is the political pressure. Now we will see the exponential evolution of the market. In the other hand, we have this pressure, and in the other hand, we have the PV technology, which are really exposed. So here, this is one graph of that describes the evolution, the exponential evolution of one technology from 2002 to 2021 in order to reach the high efficiency, about 800 watt peak. So here we can see the evolution. In the other hand, we can see that compared, we have technological evolution. We have also reduction of the cost. This graph is describing the evolution of the cost from 2010 to 2021. So as we can see, we have €2 per watt peak in 2010, and today we talk about 20 cents per watt peak. So a real exponential reduction of cost PV modules. And also we have the exponential evolution of the production. An example of an example of this manufacturing, which is predicting our PV production capacity outlook for polysilicon wafer cells and also modules, which will be reached about 50 gigawatt, and for example, the cells 113 gigawatt. So only one producer has announced already this evolution, this exponential evolution. So this is the second aspect. And the third one is the social acceptance and fake news. When I tried to see in Google what people think about PV, the dark side, I just click the dark side of PV modules. I was surprised because we have some people today that does not believe in PV and are scared about this new energy, renewable energy, calling them as, like, for example, here, toxic waste. Here is solar PV are more dangerous than nuclear. Here, how green are those solar PV module? So the problem here is people still asking question about what is the real impact of the PV modules today. So one of the questions that I have always, it is, what is the impact? What is the carbon footprint of Chinese module? What is the impact of the transport, the energy payback time, the PV storage? Are the PV module are really green? So this presentation is one of the answer is to answer this first presentation, this first question, which is what is the real environmental impact of PV technology? So what I try to do here is just have to state of art of the PV market, because in order to assess the environmental impact, we need to see what is already in the market. So I started by looking at the value chain of the PV module. Here's the value chain of the silicon PV module. So as we can see, we have a lot of brick, we have a lot of steps of manufacturing. It's a complex life cycle, which is not limited to the electricity generation. No one today as green. We have many steps. On the other hand, we have a lot of technology today. So here an example of many technology which will try to reach the higher power. So we have the heterojunction technology, the PERC, the TOPCon, etc. So a lot of technology. And in the other hand, what we already seen is the evolution for the one technology evolution of the same technology, technological evolution. So here I took this picture, I took this graph, and I tried to divide it by generation. So I call it this first one, first generation, second generation, the third, from 2018 to 2020, and the fourth one, which is the mainstream of today. And the idea here is we're gonna see what is the real impact of this technology, of this evolution, technological evolution of the environmental impact. So here, the first part, I took the 100% Chinese module. So here, this is the value chain of PV module. In order to not have the impact of the location by country, we took the mainstream, which is 100% of Chinese module. And here we have a table that describes this different assumption of the technological evolution of PV technology. So here we have the generation 1 to generation 4. And here we have the evolution of the different process of the value chain. For example, the evolution of the wafer thickness, the cell size, the module efficiency. And we will try to assess the environmental impact of this evolution. So the results are in this graph. So as you can see, this graph, it is an LCA, a life cycle assessment analysis that take into account 17 environmental criteria. So we have the carbon footprint, which is the main one today, and we have a lot of other impacts, such as the human toxicity, the resource depletion, eutrophication, etc. And so the results, as you can see in this graph, shows that from generation 1 to generation 4, we have a significant decrease of the environmental impact. So the first conclusion is the technological evolution has already an environmental decrease, significant impact on the results. So if we focus on the carbon footprint and we try to understand why we have this decrease, you can see the results in this graph, which is at right. So we can see generation 1 and generation 4, and we have the contribution of each step in the value chain. So as we can see, we have that the polysilicon and the ingot has decreased, and its decrease has an impact. So the evolution of the process, like the CMS process, which was improved, the reduction of the wafer thickness by the reduction of the consumption of silicon, for example, has helped, and also the efficiency helped to decrease the same technology by like most half or more than half the carbon footprint in kilogram CO2 equivalent per kilowatt peak. So this is the first conclusion. So today we can understand that the evolution helps a lot to decrease the environmental impact. So we decided to see what about the new technology. Here we talk about the PERC, the mainstream technology. What about the heterojunction, the TOPCon technology, this new technology that are in the even in the either in the R&D level, at the R&D level, or in already in the massive production. So we did this comparison, as you can see in this graph, to always with the 17 environmental criteria, and we compare the PERC compared to the TOPCon compared to the heterojunction technology. And the results showed that we have the more that I increase, the more I improve my technology, the less I have from an environmental point of view. Here, an example of this technology, and here we have the other, for example, in CIA, we try to evaluate the tandem technology, which is not already in the market, but we will try to anticipate the question, the environmental question. And the results shows that improvement could help to decrease the environmental impact. So the results is here. We have a decrease with the technological evolution, but we need to pay attention that all the environmental impact depends on which parameter I use in order to evaluate my module. So the question here, okay, we need, or today we succeed to decrease the environmental impact, but which parameter need also to be optimized in order to reduce more the carbon footprint? So to answer this question, in CINS, we built a tool which is called Comparative PV LCA tool that helps us in order to identify, to optimize the module to reduce the carbon footprint. It is an internal tool which is called EcoPV and helps to evaluate the environmental impact of a new technology compared depending on specific parameters. So as you can see here, we have all the value chain, and we can compare to a reference, choosing, for example, the location, choosing the wafer size, in order to see which parameter I need to focus on in order to reduce my carbon or my environmental impact. So in this presentation, I will show you some examples of the results from this tool, which with the mainstream, which has an impact on the carbon footprint. So here, for example, in the polysilicon and ingot, we have the production location, the wafer and cells, we have the wafer thickness. For the module, for example, the module power, and for the system performance, we have, for example, the location where I install my modules. So I will show you the result, the impact of this parameter on the carbon footprint. So starting by the location, the production on location, here in this table, we did a scenario where we took one reference 100% Chinese module from polysilicon to module. Then we will try to test what if I did my cell, my module in France. What if I have this scenario, for example, Germany, China, France, the scenario number 3, which is a realistic one today. We have silicon from Germany, wafer from Norway, and cells and module from France, and the optimistic scenario, everything from Norway and France, as Norway and France has the less carbon footprint, the electricity mix with the less carbon footprint. The results show for the same module, we can see that compared the reference to the scenario 3 and 4, which are here, we can reduce the carbon footprint in kilogram CO2 per kilowatt peak by almost half. So we can conclude that, for example, shifting the production of PV compound to country with low carbon footprint could reduce significantly the carbon footprint of PV modules. So this is the first conclusion. Then we tried also to test what if I did my module by recycled silicon. So here we have one step where we try to cut the ingot into brick, and today we have a value about, for example, 33%. What if, the question was, what if I increase more this value into 50, 60, and 70? So the results on the carbon footprint show that increasing the recycling silicon could reduce by 20% the carbon footprint, since I will avoid to use virgin silicon. Also, we have a question about the electricity consumption that we use in the ingot production. So here we took the production from ETR PV, and we try to see how what is the impact of this electricity reduction on the carbon footprint. So the results shown that I could reduce my carbon footprint by 25%. Next, the wafer thickness. So for the wafer thickness, I guess already this is the route that many producers use today in order to reduce the wafer thickness, in order to reduce the cost, but it helps also to reduce the environmental impact. So here what we did is we took also the prediction of HERPV, and we tried to take the assumption of, I have a reference of 170% micrometer, then the first scenario 150, 130 and 120, and we will see the impact of this reduction on the module. As we can see, for example, if I took the carbon footprint, I could reduce only by reducing the wafer thickness, I could reduce the carbon footprint by 15%. Then the module power. The module power here, we took the assumption that we will go from for a module of 120 half cells, we will take 300 watt peak to 380 watt peak. And also we did the same calculation, and the results show we could also reduce the module by 20%. After, now we finish by the module, we go to the installation location. So here we took four countries even from Europe. We have Germany, which is in the north of Europe, France, which is we can see in the middle, Italy and Spain, which are in the south. And we did the results, the environmental impact of the location variation. And as we can see, the location has a huge impact on the carbon footprint, for example, because moving from Germany to, for example, Spain, which is in the south, we could reduce by 40% the carbon footprint. So by the end, we try to gather all this assumption of optimization using our tool and try to see what is the impact. So we took European silicon production, Salian modules in France. We took 120 micrometer of wafer thickness, big glass frameless module, the bifaciality gain, high efficiency of cells, 30 years lifetime, and installation in Italy, for example. And we try to compare the whole different technology compared to this, what we call optimized heterojunction bifacial modules. So as you can see, the results compared to the PERC technology, we can reduce by 70% the carbon footprint, going from 100 to 70%. So here, for example, an example, and it's not only the carbon footprint, but it's the good news, it's all for all the environmental impact that you can see in this graph. So the optimization, all moving this parameter helps really to reduce the carbon footprint of the results, which move us to a comparison to the other energy source in gram CO2 per kilowatt hour. So this graph, I just put it just to show you today what is the position to answer the question, are the PV module are green? And the second question, how could I optimize the PV module in order to be greener by excellence? So here this graph shows the comparison between the coal energy, the gas, nuclear, and here I put many different scenarios of the PV module. So this is the first generation, which is from 2007 to 2014. Here we have the Chinese 100% mainstream module, the premium module, so the high efficiency module, and the optimized European PV module. So as you can see, the results here, if we have already the first conclusion that we are green, there is no more debate if the PV energy is green or not compared to the other source of energy. So this is the first answer today. The second answer is if we optimize our PV module using this parameter that I showed you in these slides, we can reach a competitive carbon footprint, which could reach 17. And as you can see, for example, nuclear, which is known as low carbon footprint, we are competitive to other source of energy. So we could be a solution in order to the net zero emission today. So there is no more debate. The conclusion is there is no more debate if the PV energy is the suitable solution to environmental issue. However, maybe today we need to work on other aspects like the circularity as shown in the previous presentation, the recycling of PV module in order to steal the greener energy by excellence. And for that, for example, in CINS, we try to build a circular economy of PV modules. We try to think about how to have a circular model. And when I say circular model, is try to anticipate the recycling of PV module by eco-design, try to optimize the system by responsible conception and reliability of the use, and try also to work on recycling process and valorization in order to have the closed loop of PV modules. So thank you for your attention. This is the presentation.